cloud. Okay, so it looks like we're recording. I have to unfortunately leave at 4:30, so, but since
Okay.
you're the host, that should be fine.
Yeah. And hopefully Andrea will connect soon.
Hello,
Hi, Andrea.
how are you doing?
Good. How are you?
Okay,
Okay, I'm going to make you a co-host,
okay,
and then you should be able to share your screen.
all right.
Great. Yeah.
Yeah, oh, let's go to the beginning of the talk. Okay. All right, perfect.
And then we'll just wait another couple of minutes so that we don't start before 4.
Got these lights sort of set up so that for the day, but at night there's a bit of glare. So how's it going? Are you guys all remote all the time, or?
For the most part, I think there are a couple of classes that are taught in person, but for the most part, we're remote, and we just found out we were going to be pretty much remote for the winter term as well.
We were just sent a survey. They just surveyed the faculty to see whether we wanted to come back in the spring.
Yeah, that's what we got as well.
Yeah. They haven't made it. They haven't made a determination yet. So, because I'm teaching undergrads in the spring.
Yeah, I can't imagine what it's like being like a first year undergrad right now.
Yeah.
Feel bad for them.
That's pretty loud.
They surveyed you guys. I would have thought it'd be public health measures stuff almost exclusively to make that determination if we go online or not.
Well, we got at Oregon, we just got a survey also. So I don't know how they're making those decisions.
Well, there weren't a lot of people who volunteered to teach in person, right? So it's only a handful.
Yeah.
Yeah, well, the thing is, it's not just a matter of public health, right? Because I mean, there are certain faculty who have who are immune compromised, or who are of an age where it wouldn't be that safe to do it. So it's a little bit different from, yeah.
Yeah. All right, people are still coming in fast, so let's wait another minute or two before we begin.
Okay.
I'll wait until nobody asks to join for 20 seconds or so. All right, well, maybe we should get started. So it's my great pleasure today to introduce our speaker. Our speaker for today is Andrea Liu. Andrea is coming from the University of Pennsylvania, and Andrea is a member of the National Academy of Science. Andrea started her career as a graduate student at UC Berkeley, and then, or I'm sorry, not as a graduate, as an undergraduate at UC Berkeley, got her PhD from Cornell with Michael Fisher, did postdocs at Exxon and University of California, Santa Barbara, and then was a faculty member at UCLA, and then as of 2004, I guess, the University of Pennsylvania. And if you have questions, I'm not sure the best way to handle it, but you can raise your hand or type them in chat, or depending on how things go.
Oh, butt in.
Yeah,
Please,
or just
please butt in. Then I know that I'm not speaking to a void.
Yeah, exactly.
And if some of you would be willing to keep your cameras on, that really helps me too. That there are actually people listening to me.
Yeah.
Just reassures me. Yeah.
All right. Well, with that, let's welcome Andrea and take it away.
Thanks very much. Yeah, so I'm going to talk today about work that was almost all done in collaboration with Sid Nagel, with whom I've been collaborating now for 21 years. And it's really the result of work by some really talented people who sadly have either left us or will be leaving us soon. So Daniel Hexner is now at Technion. Jason Rocks is now a postdoc at BU. Nidhi Pashin is looking for postdocs now. She's fantastic. And Carl Goodrich, who just started a faculty position at IST Austria. And part of it was done in collaboration with my terrific junior colleague, Eleni Katapori. She's really great. Okay, so so I have this title, which is maybe totally incomprehensible, like what do I mean by the malleability of disorder? So let me start out by explaining what I mean by that. And then before I get to this aspect of designing for biological function. So, so if you have, so what do I mean by the malleability of disorder? So if you have a crystal, right, there's really one large free energy minimum that dominates the properties, and we spend a whole term or two, teaching about the perfect crystal in every university physics department. Okay, but you could have a disordered system, okay, and in a disordered solid, the system exists in one of many different local minima. And each of these local minima can have somewhat different properties, okay? So, and it's that variability of the properties from minimum to minimum that actually gives you, in the end, greater tunability of standard properties, and also the possibility of tuning in very complex properties that approach what we call function in biological systems. Okay, so I'm going to start out talking about jamming because it's really the only thing I know. So if we talk about jamming as a physics problem, okay, what are we talking about? Well, we're talking about a bunch of particles, spheres, okay, and they don't like to overlap. So they're happy if they're not the energy's zero if they're not overlapping, but if they overlap, there's a repulsive interaction on them, and the more they overlap, the more they repel, okay? And then if you want to look at this thing at zero temperature, you look at the energy minima of the system, right? And you could, if you had a crystalline state, right? You could have a crystalline state, you could have disordered states at the energy minimum. You can end up, if you're at low density, having a state where once you minimize the energy, none of the particles are overlapping, so everybody's happy. Or you could end up, if your density is too high, having a state where there are unavoidable overlaps, and these red lines are the forces between the particles, the repulsive forces between the particles. Okay, so that I just explained it to you as a physicist, right? But I could have couched the same problem the way a computer scientist would have done it. Okay, so say as a computer scientist, suppose I have this this task that I want to perform, which is or this design goal, which is that none of the spheres should overlap. Okay, so how would I go about doing that? Well, those are constraints that I don't want any overlaps between the spheres. And to enforce those constraints, what I'm going to do is I'm going to come up with a cost function, okay, which means that if there are overlaps, I have to pay. Okay, and then I minimize this cost function with respect to the degrees of freedom, which are the positions of the particles, to see if I can satisfy all the constraints. And if I reach the global minimum of 0 of the cost function, then I have satisfied all the constraints. If I have too many particles, then I can no longer satisfy all the constraints, and I end up not reaching the global minimum of the cost function being 0. Okay, and this is how machine learning, this is how you do a neural network, for example. This you would construct a cost function, then you would minimize it. Okay, and you'll see like midway through the talk why I am couching it this way. Okay, but let's go back to this issue. So now if I look at the jam system, right, if I look at the system with the perfect crystal, okay, turns out that if I look at the ratio of the shear to bulk modulus at the crystal that's under compression, so I put some pressure on it, so they're overlapping. I force them to overlap, okay? And now I look at the ratio of shear to bulk modulus, you get some number, okay? Now you decrease the pressure. What happens to that? It doesn't change at all, okay? The ratio of shear to bulk modulus is constant over, for all these different pressures. Just realize,
Andrea?
yeah, that's
Sorry.
right. Yeah.
First of all, this is my first chance to say hi. Hello, this is John.
Hey, John.
How's it going? It's not completely obvious to me that this ratio is actually going to be a constant as a function of pressure, right? You could imagine the properties of a crystal changing if you compressed it a lot. Is your point just that it doesn't do anything dramatic as a function of pressure?
Correct, as long as the crystal structure doesn't change.
Mm-hmm. Okay.
Okay, so
Great.
that's right. Yeah, so for these simple potentials, it does a simple repulsion.
So there are families of potentials for which
there are
really
families of potentials where the FCC is the lowest energy crystal structure, and so if I put in the FCC and now I decompress, it's going to stay FCC until I reach, until I get to the point where they're just overlapping, and then if I let them expand some more, then the shear and bulk modulus would both drop discontinuously to 0.
Mm-hmm. Okay.
Okay. But now if I look at the disordered system, this jam system, the behavior is really different. That the ratio of the shear to bulk modulus gets smaller as I decrease the pressure. And it gets smaller as a power loss. It goes to 0 at 0 pressure. Okay. And so right away you see that the ratio of the shear to bulk modulus is much more tunable for the disordered case than it is for the crystalline case. If I think about this in a little more detail, it's useful to transform this jam packing into a network. Okay, so I'm going to put a node of the network at the center of every particle, and I'm going to put an edge between every pair of overlapping particles. So if there's no overlap, there's no edge. Okay, so I get this network, and if you look in linear response, okay, the response of jam packing with harmonic repulsions is going to be exactly the same as the response of the spring network that you made from it. Okay, and so now if I imagine decreasing the pressure on this system, okay, what am I doing when I decrease the pressure? I'm decreasing the density, and what I'm doing is I'm getting rid of overlaps gradually, and so there are fewer and fewer overlaps. And so that's like removing edges from this network. It's pruning the network. Okay. So let me think now about what is the effect of pruning the network. So imagine now taking the system, I'm just going to remove a bond. Okay, and I'm going to say, how much does that change the bulk modulus? How much does that change the shear modulus? And I can look at the distributions as I do this, okay, for how much the bulk modulus and the shear modulus change. Well, if you have a perfect crystal, right, then you just get delta functions, and it depends on the structure of your crystal, where your delta functions are and how many there are, okay? And so you think, okay, now I add disorder, what's going to happen is I'm going to fuzz out these delta functions, right? Wrong. Okay, that's not what it looks like at all. It looks like that. So for the disordered case, how the distribution of how much each bond changes the bulk modulus, okay, is broad. And the key thing is it stretches all the way down to 0 continuously. Okay. Not only that, it turns out that with some pruning for the bulk modulus, but right away for the shear modulus, okay, the distribution of how much you change the shear modulus, okay, when you remove a bond, divided by the average, is exactly the same as the distribution you get for how much the bulk modulus changes if you remove a bond. And the two are totally uncorrelated. In other words, how much the bulk modulus changes if I remove a bond is totally uncorrelated from how much the shear modulus changes. Okay, that we call that independence of bond level response. And that's really the key to what I'm going to talk about next. Okay, so what are the consequences of this? So first of all, so now I'm going to now say, I'm now going to talk about designing biologically inspired function. So the first function, I'm going to talk about two different functions today. And the first one is a negative Poisson ratio. Okay, so Poisson ratio, right, it measures the following. Usually it's positive. And positive Poisson ratio means if I pull my system this way, okay, it's going to shrink in the other directions, like a rubber band. You pull on a rubber band, it gets thinner. Okay. Negative Poisson ratio is precisely the opposite. You pull on it, okay, and it gets thicker. Now, cork is the natural system, is the biological system, right, which has a Poisson ratio of around 0. That's why it's useful for wine bottles, right? Because you push on it in this case, you compress it, and it doesn't swell or shrink, right? It just stays the same, and that's why it's useful for corking a bottle. Okay. Now the Poisson ratio is directly related to the ratio of the shear to bulk modulus. So this is the equation in d dimensions. Okay. And what you see is that the Poisson ratio becomes negative when the ratio of the shear to bulk modulus exceeds the dimensionality over 2. Okay. Which does have a negative Poisson ratio is tendons. Okay. So for example, your Achilles tendon, when you stretch on it, it actually gets wider in the other directions. Okay. And this is something extremely unnatural that most materials do not do this. Okay. This is special.
Andrea,
Yeah.
is there some biological advantage to having a negative Poisson ratio for your tendons? I mean, is this something that evolution picked out because it helps you in some way? Or is it just
Yeah.
a weird...
So definitely for compression, it's helpful. You know, so for compression, suppose you compress, it's certainly good for impact. So if you, and in fact, NIST ended up funding Sid and Juan de Pablo and stuff like, and a bunch of them at Chicago to design better football helmets. Okay, the resistance to impact that have negative Poisson ratio. So the idea is that when you push in here, it doesn't bulge out elsewhere.
Because if it divulges out elsewhere, it could potentially rupture.
That can do damage.
Mhm.
So yeah, so you actually want a negative Poisson ratio football helmet.
Mhm.
Okay.
Huh.
And that could be yeah, I actually looked for tendons and I couldn't see any. I just found measurements that said that it was negative, but I didn't find things saying that that was useful biologically for the tendons. Yeah, but presumably it is good for something like you know, impact.
Mhm.
Okay. All right. So now, all right, we got our networks, and can we design our networks, these mechanical spring networks, to have a negative Poisson ratio? Okay, can we do it? So I'm going to introduce the idea of an edge demon. Okay, and so the idea of an edge demon, it is something that can go in and clip whatever bond I want. Okay, I'm going to call that a pruning edge demon in this case, because I'm cutting a bond. So let's suppose I take my pruning edge demon and I just go there and cut totally at random. Okay. In that case, I'm removing bonds that, as far as the shear modulus is concerned, they're removed at random. So it's like removing from the mean of the distribution. And same thing for the bulk modulus. And they have the same distribution. So the ratio of the shear to bulk modulus is constant. Okay, as I prune, stays constant. But now I'm going to go in with, let's say, greedy pruning demon. I'm going to prune the one that makes the biggest difference to the bulk modulus, the biggest drop to the bulk modulus. Well, as far as the shear modulus is concerned, I'm removing something from the mean of the distribution because I'm removing it at random. So the bulk modulus is now going to drop much more rapidly than the shear modulus. And the result is that the ratio of the shear to bulk modulus is going to go shooting up. Okay, very, very rapidly. And once it reaches, remember, the dimensionality over 2, 3/2 in 3 dimensions, okay, I've got negative Poisson ratio. Okay, so I can do the same thing by, instead of pruning the bond that changes the bulk modulus the most, I could prune the bond that changes the shear modulus the least. Because that distribution, remember, is continuous all the way down to 0. So that doesn't change the shear modulus at all. But as far as the bulk modulus is concerned, I'm removing something from the mean, the distribution. Okay, so again, the bulk modulus is going to drop faster than the shear modulus, and the ratio is going to go up. Okay, jamming turns out to be removing the bond that changes the bulk modulus the least. Okay, and that gives you jamming scaling and so forth. Okay, so because I'm decompressing the system. Yeah.
Is there a simple way to see that jamming is equivalent to removing the one that changes it the least, or is that just an empirical observation?
I think because jamming is formed by compression. You jam by compression. And so if I decompress the system, right, I'm just losing the overlaps that were just on the verge of going. So I'm pruning the ones that had the least overlap and changed the bulk modulus the least.
But you also change the shear modulus when you do that.
But as if I'm changing it as at random. In other words, what I'm doing when I decompress the system is I'm losing overlaps.
Right, but if you lose an overlap, doesn't it change the shear modulus?
Okay, so yes, so it turns out yes. So what did So you have to look at the projection of the kinds of deformations you get under compression onto this versus shear. Okay, and it's primarily the compression when you lose the overlaps.
Okay, but there's some reasoning that has to be gone through.
Yes, there is some reasoning. Yes, it is. You're right. It is not simple.
Completely obvious.
Yeah, it is not obvious. True. Yeah.
But it's true.
But it is true. Yes.
Okay. Gotcha. Thank you.
Okay. All right. So this is great, right? Let me just point out that look at the scale of this. This is 20 orders of magnitude. I can get a 20 order of magnitude difference in the ratio of the shear to bulk modulus, fiddling with only about 1% of the bonds. Okay, this is fantastically sensitive, fantastically effective. Okay, and tuning the mechanical response. So this is great. Okay, except it's great on the computer, but it's not great in the lab, or, you know, for one thing, it's not scalable, right? I have to, as my system gets bigger and bigger, I have to be able to figure out, okay, which bond is it that's going to change the bulk modulus the most in order to be able to clip it, okay? And that's going to take longer and longer as I scale up my system. Another thing is I have to know everything. I have to know all the microscopic details perfectly in order to be able to calculate which bond is it that's going to change the bulk modulus the most. And then finally, I had to be able to go in and I had to clip it. I had to have that ability to clip it, okay, the one I want. So then it seems like, okay, well, that's sort of interesting, but not that useful. Okay, so is there a way to exploit this malleability disorder without actually knowing and directly manipulating with these edge demons, okay, that can do everything at the microscopic level? So, and of course the answer is yes. So it turns out that you get almost the same results if instead of pruning them.
Andrea, can I ask a quick
Yeah,
question?
please.
So you mentioned that the daemon has to identify, in a sense, which of these bonds actually does these maximal, optimum, or extremum changes. But presumably there are also bonds that are, you know, delta below that change. In other words, they're the second best bond, but how, I guess I'm wondering, like, what is the distribution of bonds that are close to that optimum bond? So it widens the set of things that you could cut, the daemon could cut, that would actually result in something very similar.
Exactly, yeah. So that was this distribution here. So you see, there are bonds near the maximum. And there are lots and lots of bonds near the minimum if I want to prune the minimum. That's right. So you don't have to choose the one that changes the bulk modulus the most. Oh, gosh, don't want to give away the fun part. So there is a way to go after bonds at that high part of the distribution. Exactly what you were saying. And that is put on a stress on the system and see which bonds are under the most stress. And that's almost the same, okay? Those bonds tend to be very high up in that distribution. And so if you have a system where bonds just break once they get above some threshold stress, okay? Then if you apply an isotropic stress, expansion or compression, okay, then the ones that are under the most stress are the ones that would tend to change the bulk modulus a lot. And so if you apply an isotropic stress and they start breaking, your system will automatically tune itself to have a negative Poisson ratio, okay? If instead you take that same system and you apply shear stress, then the ones that break are going to tend to be the ones that change the shear modulus the most, and you're going to tune yourself to the opposite limit of the highest Poisson ratio you can have, or the shear to bulk modulus going to 0. Okay, so you can automatically tune yourself between these two limits. And the same thing goes, just like you can prune the minimum bond and get to where you want, right? The one that changes the shear modulus the least, you can also make the Poisson ratio go negative. So you can, if you have bonds that break below some threshold stress, and now you apply shear stress, okay, then the ones you'll break are the ones that change the shear modulus the least, and that also takes you into negative Poisson ratio. Okay, so that's starting to get to be something that you could do, right? That if I were a gifted polymer chemist, I would know how to design, and actually these systems actually exist where bonds in the network break above some threshold stress. Okay, so presumably you could take those systems and now stress them and have them tune their mechanical properties. But biological systems actually do that. Okay, so biological systems actually have pruning edge demons. Okay, so this is a picture of a bunch of cells. So the blue things are the nuclei, the green are microtubules, and what I want you to focus on is the red actin cytoskeleton. Okay, so this is a network of actin filaments, and the thing is that there are, first of all, severing proteins like cofilin, okay, that bind onto actin and cut it, and they purposely cut filaments that are under low tension. There are also cross-linking proteins, okay, that if you have a cross-linking protein that binds two filaments together, now you put this junction under stress, they can just pop off, right? Because they have some binding energy. So, so these networks are reconfiguring each other, getting cut, changing their cross links all the time in vivo, okay? And people have not really thought about this before, and I keep trying to get somebody to do an experiment to say, you know, the system must be tuning its mechanical response as it does this, okay? Because these things are there, and these things must be changing that mechanical response. Another example is collagenase. So collagenase is an enzyme that cuts collagen, which is what makes up your tendons or the intracellular matrix. Okay, and collagenase preferentially severs collagen that's under too low tension, and also can sever collagen that's under too high tension. And so this thing about severing under too low tension has been, you know, called, oh, it's use it or lose it, right? If it's nature being thrifty, if the collagen filament is not under much tension, then might as well cut it and use that collagen somewhere else. Okay, but what we're suggesting is that maybe it's more than that. Maybe it's also lose it in order to use it, that by losing it, you are actually changing the mechanical response of this collagen network, okay, which may be useful. So, so I think these are some open questions. So, but I think it must be that these pruning edge demons help make the mechanical properties very adaptable. Yeah.
Yeah. So the way you've been discussing this so far, at least the way it seems like you think about this is you imagine you do this cutting process and you compare the mechanical response of the system before you did the cutting to the mechanical response after you did the cutting, right? And what I'm wondering is, suppose you're changing the way you shear the system on the same time scale that the cutting process is happening. You know, so suppose I'm shearing this thing on a time scale comparable to the time it takes the cofilin to go in and sever the actin. What I'm wondering is, will I see some frequency dependence in the mechanical response of this? So such that if I shear it with a rapidly oscillating shear, I don't see the effects of the cutting, but if I shear it with a slowly oscillating shear, I do see the effects of the cutting. And the reason I ask that is I seem to remember that people who studied the elastic properties of these biological networks find that they have rather unusual frequency dependence. And I'm wondering whether part of that could come from this.
Yes, and in fact, there is a recent paper by guys Kundrik and Fred McIntosh, where they have, and I think it is actually cofilin with actin in an actin network, where they are seeing a very interesting frequency dependence that that could be due to this. Fred and I actually talked about that. Yes, yes, okay. I think that's exactly. I think you're exactly right. Yes.
Cool. So, and it could, one could also imagine in biology that frequency dependence could be something important too.
Yes, that could be useful too. Exactly. Yes.
Wow. Wow, yeah. You get a lot out of this.
Yeah.
Huh. Cool.
Okay, so when I think about what's
sorry, if I could,
yeah.
like kind of related to that, I mean, this isn't a well-formed question, so it may not make a whole lot of sense. But I mean, in the case of like actin networks and like cofilin and stuff, I mean, you know, we can't think of these as sort of networks that are sort of you know, a stationary cartoon that then like cofilin is coming and breaking, but rather, you know, actin networks are always very dynamic. They're, you know, polymerizing at one end, depolymerizing at the other, and I believe like cofilin acts at like at one of those ends and is causing it to like destabilize like from the end. I think. So does that?
Yeah.
Or maybe it also severs. But in any case, does the fact that these are always growing and shrinking alter this picture? And maybe this comes to John's thing about, and what you were saying before about frequency. Is like frequency dependence a consequence of the fact that the whole thing is constantly dynamic?
Yes, this whole thing is constantly evolving. And as it's constantly evolving, its mechanical properties are also, what we're saying is the fact that the network topology is constantly evolving means that the mechanical response is almost certainly also evolving in this non-trivial way.
Okay.
Yeah.
Okay.
Along with it. Yeah. Yeah.
Thanks.
Yeah, really good point. Okay, so so I got this system right now. I'm putting it under stress. It could be in my actin system, or it could just be my original thing, but with things that break above some threshold stress. And if I think about that, that's really an aging process, right? In other words, I put on this stress, and then I just watch these bonds go pop, 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 right? And the system is evolving as it does that. So it's aging under this stress. And because the system is disordered, right? The system is aging. What we're saying is the system is aging in a way that depends on the stress state. Okay, so can we use that now to control properties of real systems? Okay, so these are systems that Needy made in the lab, in Sid's lab. Okay, so they start out with this solid foam, and they cut out things inspired by jam networks. So they started out with the same initial jam network in each case. And this thing on the left, okay, they shrank the particles a little bit, cut them out, and then had little bridges connecting particles that are overlapping. Okay, and this system is like the thing I told you, where I have nodes at the center of every particle and edges connecting every overlapping particle. And this thing, the holy sheet, okay, is where you cut out, you have holes, you shrink the particles, and then you have holes where those shrunken particles are, and you have then solid foam in between. Okay. And so now what they did was they just took the system and you just compress it. It's exactly what I said. You put it under isotropic compression, and now you wait. And the whole idea, right, is that in this system, the parts that are under higher stress are going to deform faster, okay, than those that are under lower stress. So that's nature. Okay, nature is providing the edge demons, okay, or doing whatever it is so that regions that are on higher stress are relaxing faster. Okay, and does it work? Yes. Okay, so here's the ratio to shear to bulk modulus for the three systems. In all three cases, it goes up. The least exciting case is jam packing, where it only goes up a little bit. But in the other two cases, the network and the holy sheet, it goes well below this solid line, which is where it becomes negative Poisson ratio or auxetic. Okay. So these systems do develop a negative Poisson ratio. So it works. It really does work. And this is a much more complicated system than the simple network of springs, right? Central force springs. This is a real system. So it's quite robust. So if I think about this system, okay, I can think if I think about it in terms of a simple central force spring network, I can think of two things that are happening, okay? First, the spring constants themselves are changing. And secondly, the network geometry, how long the springs are, is changing as these things deform. And so it's like saying the equilibrium lengths of the springs can be changing. Okay, how can you test that? Well, what she did was she took the final system, okay, which has a negative Poisson ratio. She took a picture of it, okay, then she laser cut out an identical network. So it has the same geometry, okay, but all the spring constants are from the fresh foam. So this is something where the spring constants couldn't evolve, okay, but the network geometry had changed because of the compression, because it came from a picture of something that aged under compression. And what you see is that this copy of the system, the Poisson ratio, this is Poisson ratio now, again, it still went negative. Not as strongly as the age networks, but the geometry change alone was enough to give you this, even without changing the spring constant. So that suggests, so that sort of inspires these models. And I'm going to focus here on what we call the L model, which is the one for the equilibrium lengths. So the idea is if I take the equilibrium length, if I take a spring and I put it under tension, its equilibrium length wants to increase. And if I put it under compression, its equilibrium length tends to decrease. Okay, just do that. That's actually been shown to be a decent model for what happens in tissues. I can talk more about that. But that's actually very similar to models that people use for bone, which we know remodels itself under stress. That's right. That's why you want to jump up and down and put a lot of impact on your bones to increase your bone density. Okay. So now if we take this model, okay, where the equilibrium lengths respond to the stress on it, okay, here's another strategy to get negative Poisson ratio, which we call driving while aging. Which is something if you have aging parents, you don't want them to do. Okay, so here's what you do. We're going to put on what we want is we want to, if we put on a source strain, which is, for example, this compression side to side, then what we want is a negative Poisson ratio. So we want to have a target strain, okay, which is the same as the source strain, same in magnitude. So we want to get a Poisson ratio that's as negative as it can be, which is -1. That means if I compress this way, I end up compressing in the other direction by the same amount. Okay, so how do you do that? What you do is you take this system and you put it under cycles of isotropic expansion and compression, expand, compress, expand, compress, and all the while the equilibrium lengths are responding according to the stresses that are on them. It's a purely local rule that each spring just says, oh, am I getting stretched? Okay, I'll get longer. Am I being compressed? Okay, I'll get shorter. Okay, and it's just doing that, and you're just going like this, expanding, compressing. Okay, and darned if that doesn't work. Okay, so here's the unaged system. This is 0. Okay, after 500 cycles, 1,000, okay, enough cycles, and it reaches -1 over some range of strain. And this is not the linear regime. These are big strains out of the linear response. Okay, so we can even train nonlinear response. Not only that, so now I'm showing you the Poisson ratio that you reach after 50,000 cycles of strain. Okay, but I'm doing this, I'm training the system in 3 different ways. So for the blue system, I'm doing my isotropic compression and expansion, okay, between the 2 blue lines. So a small expansion, a small compression, small expansion, small compression, and I get the blue curve. The green one, I'm applying a larger amplitude isotropic expansion compression cycles to age the system. Okay, and the red one is where I applied the biggest amplitude of expansion and compression during my aging. And what you see is that for the blue one, the Poisson ratio is near -1 between the 2 blue dashed lines, which were the strains that limited my the amplitude of my periodic strain that I was driving the system while aging. Okay, the green one is flat and close to -1 between those two green dashed lines. And red, you see, it expanded. So I can look at the response by measuring the Poisson ratio after it comes out at the aging. I can read out the strain at the amplitude strain at which the system was aged, was prepared. The system has a memory of how it was prepared. It remembers, and you can read it out. Okay, and the larger the amplitude of your thing, okay, the bigger the region over which it'll reach the maximum negative Poisson ratio of -1. Okay, and you can make that well into the nonlinear regime. Okay, so that's the first section, tuning negative Poisson ratio. Okay, and this was so effective. Okay, that we said, okay, how far can we push this? Can we do something else? Okay, so so here's our second biologically inspired function. Now we're going to get a little fancier. This is allostery. So a lot of proteins do this. Enzymes and signaling proteins, most of them use allostery to achieve their function. So the idea is the following. Suppose this protein is an enzyme. So I've got this molecule, this red molecule, and wants to come, and if it's bound to the enzyme, it can get hydrolyzed or phosphorylated or something. Okay, some chemical change, and it goes off happy. All right. But here's a protein where the enzyme is turned on by allostery. So the idea is that originally the substrate molecule cannot bind. But if this other molecule, different kind of molecule, if this regulatory molecule binds over here, okay, then it induces a conformational change over here that enables the substrate molecule to bind. And so now I turn the enzyme on. Man-made catalysts can't do this. You can't turn them on and off at will, okay? Biological catalysts are much more powerful because of allostery, because you can turn them on and off. And you've got other ones which work the opposite way, where it can bind, but if the regulatory molecule is attached to it, then it cannot bind, so that turns the enzyme off. Okay, so if I think about, and the weird thing about allostery that has stumped people since the 1950s, okay, is how can you get this response way over, usually often on the other side of the protein, pretty far away on the protein, okay? And you say, okay, well, let's think about it in physics terms. Well, what I'm doing is I'm applying a source strain over here, okay? And I'm getting a target strain over here, which is comparable to the source strain. And you say, okay, elasticity, it's long range, no big deal, right? But deformation actually decays quite rapidly with distance. So for a protein-sized object, what you would expect normally is that the strain over here in response to a strain here would be down by a factor of 10 to the minus 2, 10 to the minus 3. Okay, so to have a response of order 1, about the same order as the source, is strange. Okay, that's special. Okay, you don't just get that. It doesn't just happen. So the question is, can we design it using our edge demons? Okay, so let me just first point out that if you wanted a localized strain due to at the target in response to something at the source, the best design for this function, I would argue, is something that the Chinese figured out a long time ago. Okay, you would want something like this, okay? But oddly, most proteins don't look like that, okay? And what that says is that their design really is not optimal for allostery, okay? I'm gonna now talk about a different example, which is also not optimal. So here's, and this is due to my fantastic colleague, Eleni Catafori. So So she heard me talk about this stuff and she said, oh, you know, the same thing happens in the brain. The brain, the system of blood vessels in the brain. So blood comes in through the arteries into the brain, and the brain, you know, the volume of the brain doesn't change. You don't want to have suddenly a lot of flow in the brain. So it's actually very tightly controlled, okay, the amount of blood flow in the brain, okay? And the other thing about the brain is that it uses a fantastic amount of oxygen. It uses 25% of the oxygen that comes into our bodies, okay? Even though it's only 2% of the body mass, okay? Now, why is that important? Because depending on what you're doing, okay, like I'm talking right now, that means my speech cortex needs more oxygen. And the way the brain gets more oxygen to the speech cortex is by delivering more blood flow there, okay? And how does it do that? It contracts and dilates individual blood vessels to do that. So what that's saying, this is a network, okay? Where instead of a network of springs, I have a network of blood vessels, and their conductances through their diameter, right, are being tuned in real time to direct flow from the source, the target, the arteries, to a target, the speech cortex, okay? But now suppose I stop talking and I start walking, right? If I start walking, this is the terrible thing about not actually being in front of you in the audience, then I could really walk. Now I can only walk around a step at a time, right? But, you know, if I start walking, I need enhanced blood flow going to a different part of my brain, okay? And so then the blood vessels again adjust to send the blood flow there, okay? So the optimal design, right? If you had a source and a target as a straw, right? But that's not what the brain looks like, and that it can't look like that because I can't totally destroy the vasculature and build a new straw every time I want to do a new task, okay? So that means the design cannot be optimal for any given target. So what is the design principle here? Well, I'd say maybe it's adaptability, okay? Maybe the idea is that the brain vascular is, the architecture of the network is such that it's really easy for it to send, it doesn't have to change the blood vessels very much in order to send blood flow to wherever it wants to go, okay? And so what do I mean by adaptability? Oh, first, yeah, let me just finish that. What do I mean by adaptability? Okay, I'm going to say, well, first, it's possible to do it, that when I want to send it to someplace else, I can do it. And the second thing is I should be able to do it without too much effort. Okay, and we'll want to quantify that. Okay, just to say that, you know, it turns out that the flow network and the mechanical network had the same mathematics. And the easy way to see that is in the mechanical network, when you're in mechanical equilibrium, the net force on each node must be 0, right? No acceleration on each node is at rest. So, so the net force is 0, whereas in the flow network, when it's in equilibrium, right, I have Kirchhoff's law. No net current at any node, okay? And those sort of conservation laws or those constraints basically make the mathematics reasonable. Okay, they're both governed by a Laplacian. Okay, so basically flow networks are like a 1D version of mechanical networks. Mechanical networks, I have vector forces, and flow networks, I just have this scalar current. Okay, so what we're going to do now, how do we test to see whether these things are adaptable? Okay, there are different strategies you could use at this point. Okay, we're going to just start out with ensembles of flow or mechanical networks. We're going to either design allostery as in protein allostery, where it's a strain, or what I'm going to call flow allostery, where I have a source pressure drop and I want a desired target pressure drop. Okay. And so the idea is we're going to start out just with ensembles and networks. And these are just going to be the networks that we got from jam packings, because that's what we have lying around. Okay. And now what we're going to do is each network in this ensemble, we're going to tune function into it, allosteric function into it, using the edge demons. Okay. And then what do I mean by adaptability? Two things. First of all, what fraction of these networks can we tune successfully to have that function? And secondly, how much tuning is required in order to achieve that function? And the idea is if almost all the networks can be tuned successfully and not much tuning was needed, then it's pretty adaptable. Okay, so, and this is what the strategy we're going to use. It's different from the strategy, it's not taking a real protein, and there is actually a healthy community of people who take real protein, folded proteins, and turn them into mechanical networks and study their properties. We're not doing that. Okay, you could do that, but there aren't that many proteins out there. And if you want to look at the same protein, you can look at it across species, but there are not that many realizations. We can generate thousands and thousands of networks, as many as we want, and design the same function into all of them and look at and see what happens. Okay, and that's, I think, a huge advantage. So how are we going to do it? This is where it helps to think like a computer scientist. Remember, I introduced jamming as a computer science problem. Well, now we're going to solve this the way a computer scientist would. We're going to say our constraint from mechanical network, let's say, is I'm going to apply a source strain, which I'm going to call 1. Okay, I'm just going to call that source strain 1, whatever it is. And my constraint is that I want the target strain to be at least delta. Okay. How do I do that? I penalize myself if my target strain is less than delta. Okay, so I design a cost function where the targets, or I have the target strain and I compare it to delta. And now I change my degrees of freedom. I adjust my degrees of freedom to minimize this cost function. And what are the degrees of freedom? Well, if I'm pruning bonds, my degrees of freedom are each bond can be present or absent. Just a binary variable. Or I could tune the bond stiffnesses continuously. Or I can tune them in discrete steps, all different versions of this. Okay, like spin models. And so now I can tune these degrees of freedom to minimize this cost function. And if I reach the global minimum, then I will have succeeded, right? If I reach a global minimum of 0, then my target strain will be what I want. Okay, and I'm going to use my greedy edge demons to minimize this cost function. Take the biggest step down that gradient to minimize this cost function. And that works. Okay, so here's the same network. In this case, it's a mechanical network on the left. On the right, it's a flow network. So in the mechanical network, I apply strain across these 2 red source nodes. Okay, and what's up here in the left corner is the strain between the 2 target nodes. Okay, so, and now I'm starting to adjust my network. I'm changing my bond stiffnesses. The blue dashed ones are the ones that get removed entirely. Okay, they get entirely pruned. And as I do this, the target strain goes up and up until it reaches the source strain. Okay, here's the flow network, the same network. I just now turn it into a flow network. The pluses here are those are the node pressures. They're either positive or negative. The size of the symbol tells you how big it is. Again, the blue dashed ones are edges that are completely removed. And as you see, as I tune this, as I minimize my cost function, the pressure drop across the target rises until it reaches my desired pressure drop, which was, in this case, was 0.2. Okay, so it worked. The thing that was shocking to us at first was how easy it was to get it. So that in a network, this is for pruning. These numbers are for pruning, just removing edges altogether in a mechanical network. Okay, if I wanted a response delta that was the same as the source, okay, the success rate was well over 99%. Almost every single time we were able to do it. okay? And if you looked at the fraction of removed edges, it was tiny, so that in a network with 1,000 nodes, okay, which is not unreasonable for a protein, you had to remove on average 5 edges. It's almost nothing, okay? So I would say allostery is a highly adaptable function, okay? It's really, really easy to tune a network to have allostery, okay? And you can succeed almost all the time, okay? This actually works. So again, this is a real system made by laser cutting by Needy, okay? And those are the source nodes, the target that I was pointing to, and now I put a strain across the source, and you can see the target moving, okay? And you can make 3D realizations as well by 3D printing. Okay, and you can do it by driving while aging. This is the cool thing. You don't have to have edge demons again, okay? You can do it just by driving while aging. So again, I have this rule that the spring, the equilibrium length increases if it gets stretched and decreases if it's compressed. And here's my source and here's my target. So what I'm going to do is I'm going to stretch both the source and the target, or maybe they're out of phase with each other, I forget. Okay, so I think in this case, maybe I think they're out of phase with each other. Okay, so when the source gets short, the target gets long. Okay, so they're being driven like this. Okay, and as they're being driven like this, you're applying this aging rule. Okay, and what we're plotting here is that after like several cycles of this, you stop and you do a test cycle. Okay, which is plotted here. So the green is what the source is doing. Okay, it goes between -1 and 1 in these units, and the red is the target. And you can see that as you do more and more cycles, the response at the target. So to measure this, I'm only driving the source. I'm not driving at the target. I'm measuring what's happening at the target. Okay. In other words, I do 10 cycles where I do both. And then I do 1 cycle where I just do the source and see what the target's doing. And that's what I'm plotting. Then I do 10 more cycles of doing both while aging. And then I do 1 where I'm just measuring what the source is doing, and then I get this. And it just goes up over time. Okay, the target response is approaching the source. I am tuning in allostery. Okay, it works. Oh, I'm almost out of time. Yeah.
Okay.
Yeah, so I'm just almost out of time. Let me just say that, we're all consumed with trying to multitask and do many things at once. Okay, so now I want to be able to actually think while I'm talking to you, ideally. Okay, how hard is it for my brain to send flow to 2 places at once? Okay, and so we looked at what is the limit of multifunctionality, and turns out that it's got the same properties, almost quantitatively the same for flow and mechanical networks, but in particular, you see that in the large system limit, it becomes a first order phase transition, but with non-trivial power laws. Okay, it's a constraint satisfaction transition. And so the limit of multifunctionality is actually a phase transition, okay, where it now cannot satisfy anything. But I also want you to call your attention to the numbers, okay? So in a system, okay, with 2,000 nodes, okay, I can tune hundreds of targets simultaneously, okay? So tuning 1, I'm way over here. This is the probability of success, okay? How many times, how many networks actually satisfied the constraint, okay? Achieve success in tuning allostery. And the idea is if I'm tuning 1, it's way down here, okay? It's way, way below the phase transition, okay? And so that's the idea, that's why tuning 1 is so easy. It's because the limit of multifunctionality for a network of that size is actually hundreds, okay? And so real networks, flow networks in the brain or proteins should operate well below that limit in order to be adaptable. Okay. And this limit of multifunctionality is in fact a constraint satisfaction transition, much like, rather similar to the jamming transition. Okay, I'm going to skip that fun stuff and just sum up. Okay, so so now I'm going to do some stuff that's below what Sid calls the bullshit line. I'm going to start bullshitting. Okay, so so the idea is that we found that it was really very easy to do it. We hardly had to tune the system at all in order to get allostery. And I think that raises a question. Could that be why so many proteins have managed to evolve allostery? Okay, because it's actually pretty easy. You don't have to do that many adjustments to evolve allostery. So what I want to leave you with, this idea is that these are two types of networks, but there are many, many networks out there, right? There are biochemical signaling networks, there are ecological networks. An ecological network, right? You introduce wolves into Yellowstone and the beaver population goes up. That's like allostery. Okay, I mean, you're getting something at the source and you're getting something at somewhere else, right? Neural networks, you train a neural network, okay, with images of cats and dogs, okay, and out comes the word cat or the word dog, right? That is allostery. That I can think of as allostery. So allostery is sort of like a Green's function. When we think of a point source and a point target, it's like a Green's function for this thing, and you can build up very complicated responses from it. And the idea of it itself, allostery, is sort of portable from one network to another in a way. And so I think it's worth asking, well, how general are these ideas? Okay, thanks once again to the people who actually did the work, because all I do is talk, as John and Eric know. And so, let me end by thanking them, and thank you for listening to me.
Thank you, Andrea. So we've got a little bit of time for questions, but also I think, if people want to stay, they can have, more one-on-one discussions. Also, I want to point out that Andrea will be available to meet with all of the women in the physics department, and I guess, in general, any women in natural sciences tomorrow at noon Oregon time. Is that correct, Andrea? I think it is. But
I think so.
Yeah.
Yeah.
But please, if there are any questions.
I have a question. Hi.
Hi,
related to the last thing you said. So you talked about kind of this beautiful work with networks that are kind of close to jamming, based on systems close to jamming, and but then there are all these other networks, in particular some of these neural networks used in, say, machine learning, are very densely connected. Whereas the jamming networks, they tend to be kind of sparse in some sense, right? They're close to some kind of threshold. So is that important for this kind of learnability in the kind of things you were talking about? Is the sparseness important, or could this also work if everything were highly connected? I was curious about that.
Yeah, so it's interesting because the more highly connected it is, of course, the more you have to potentially tune in order to get the function. But the really interesting thing about deep learning, they start out with these huge connections and they want a huge number of edges. And the reason why is because you want the number of your degrees of freedom to be huge compared to the number of constraints, so that you can really easily reach the global minimum of your cost function. Okay, so that's why they do that. But now they the network learned something, okay? And now they can go in and they can start pruning. And it turns out that you can prune a huge fraction of the bonds without actually destroying that. So they weren't actually necessary.
Oh, interesting. So after the learning, after the neural network has been trained, it actually is sparse effectively?
It actually is sparse effectively.
I see.
Yeah.
Interesting.
And so that if you knew how to design it to be sparse in the first place, you wouldn't have needed all of those. And those are there just to get you there very easily.
I
Okay.
see.
But they're actually not necessary.
Huh, cool. Thank you.
Yeah. So they're more similar than I thought at first. Yeah. That's a great question.
I have a question. So earlier you were talking about how you prune the bonds with the highest ratio of bulk modulus to shear modulus to make oxidic packings. And then you talked about the biological processes that, you know, cut bonds based on tension. And I was wondering, this might be a dumb question, but is that actually similar to the bonds with the highest ratio of bulk modulus to shear modulus?
Yeah, it's extremely similar. So in fact, that's what we did at first with Carl Goodrich. We were pruning the ones that were under the most stress. And that's, you know, we discovered this incredible tunability. And it was only later that we realized, oh, theoretically, it was much easier to understand and we could, you know, actually do things much more cleanly if we looked at what changes the modulus the most. Then you can actually derive the, you know, you know, you can do some nice theory, which I didn't go into today. But yeah, but it's almost the same.
Now, Andrea, is it easy to understand why that's almost the same? Why the high tension bonds are the bonds with this greatest ratio?
Yeah, because basically what you do is you look at the projection of the kinds of deformations that you get under compression onto, basically onto the states of self-stress. Okay, and so yeah, so when you look at that, then you can say, okay, which bonds are under the most stress? You can actually show that those are highly correlated with the ones that are involved in this sort of projection.
Thanks.
Yeah, it's possible to show it. I don't think it's totally. I wouldn't say it's totally intuitive that I can say that and you say, oh yes, of course. Okay, but the point is, yes, it does come out to be. They come out to be highly correlated with each other.
Well, if there aren't further questions, then maybe we should wrap things up and just thank Andrea once again for a really lovely talk and for sharing her time with us. So thank you, Andrea.
Thank you.
Thank you. That was fun. Fun audience.
And all right, and
Okay.
I'll end the meeting for everybody. So goodbye.
Yes. Okay. Bye-bye.